we sort of defined what a solution was, okay, and we explained solubility and the different trends. Now let's look more into the energetics of a solution. Okay, here's what's involved here. Let me maximize this. We've kind of already gone over this before. Remember that the solute is attracted to itself. The solvent is attracted to itself. And what needs to happen is that the solute and solvent need to be attracted. Okay? So basically, the solute needs to break the intermolecular forces to itself. The solvent also needs to break intermolecular forces to itself. And then it needs to form new intermolecular forces between the solute and solvent. Okay? To break intermolecular forces, that's endothermic because you need energy, and to form it is exo. So let me kind of see if I could draw this. There's a video I posted, probably a whole lot better, that shows you a solution mixing. So let's say I have, I'm just going to put dots. Here is the solute. Let me first draw my water. There. Okay. Let's say, I guess let me convert. Here's my solute, and these are little intermolecular force lines here. Okay, so it's attracted to itself, and these lines are the intermolecular forces here. Okay, and then here are my water molecules that are also attracted to each other. Okay? Oops, whatever. Okay, so this right here is my solute. So right now we'll call it sodium chloride. And this is my solvent. We'll call it water. And right now they're separated. They're not mixed. Okay, so in order for them to mix, all of these intermolecular force lines here need to break. And all of these intermolecular force lines need to break. So the solute intermolecular forces need to break, and the solvent intermolecular forces need to break. Okay? And then they need to start forming new solvent-solute lines. So now I need to break these, break, and form new intermolecular forces between the solvent and the solute. Okay? They need to form these intermolecular forces so then they mix. Okay? So that's what we're going to be looking at, the energetics there. So, let's go back. PowerPoint. So here is the this Hess's law. Remember, where you could add up all the different enthalpy. Enthalpy is delta H. Remember, that is just the energy in form of temperature, basically, to make and break bonds. So we're just going to add all of them up. So we need to look up how much energy it takes to break the solute bonds, intermolecular forces. How much energy does it take to break the solvent intermolecular forces? Okay? And then how much energy does it take to form the mixture, so the solvent-solute bonds? So here's an example here. If the enthalpy of solute is 50 kilojoules, okay, so let's see, write it over here. Delta H, which was it, solute? I wish I could just remember. Solute is 50, and delta H, the enthalpy of solvent, is 100. Solute equals 50 kilojoules. Delta H solvent equals 100 kilojoules. Okay, and the enthalpy of solution is negative 50. Delta H solution equals negative 50 kilojoules. And it wants to know mixing. What is the enthalpy of mixing? Okay, so this is what it tells me here. It takes 50 kilojoules to break the solute, Okay, so those intermolecular forces, it takes 50 kilojoules of energy to break those. It takes 100 kilojoules of energy to break the solvent. Okay, and when I form everything together, it releases 50 kilojoules of energy. Okay, so let's figure this out. Solute plus solvent plus mixture equals solution. Okay, so let's just put that up here. Delta H of solution equals to delta H solute plus delta H solvent plus delta H of the mixture. Okay, and we're trying to find delta H mixture. So how much energy is formed when we have the mixture? So let me change the color here. So we have delta H of the solution right here is negative 50. So we're going to put in negative 50. Okay. We have, and notice that all our units are in this correct unit. Kilojoules, kilojoules, kilojoules. They're all the same. That's good. Delta H of the solute is 50. Plus delta H of the solvent is 100. Plus the mixture, that's what we're trying to find. Delta H mix. Okay, so let's add these. 50 plus 100 equals to 150. So negative 50 equals to 150 plus delta H of the mixture. Okay, now let's bring this over here. It's a positive sign here, so we bring it over. It'll be a negative. So we have negative 50 plus negative 150 equals delta H of the mixture. Okay, so this will be negative 200 equals delta H of the mixture. And what are the units? Kilojoules. Okay, so whenever I make the mixture, it's going to release 200 kilojoules of energy. And that's good. You want to release energy into the atmosphere. That's what it wants you to do. So that's favorable. If you take energy from the atmosphere, so that'd be a positive sign, that's unfavorable and it won't actually happen. It won't mix that way. That means it's insoluble. If you have a negative, though, that means it's going to mix. Let's do another one of these. Let's see, I pulled it up. Word. Here it is. Oh wait, we haven't gone over heat of hydration yet. Let me define a few more things first. It's in this next one. In an aqueous solution, so that just means something in water, what they do is they combine the delta H of the solvent and delta H of the mixture, and they just call it delta H of hydration. Okay? So basically, instead of saying delta H solution equals delta H solute plus solvent plus mixture, it's actually just the solute plus hydration. So they combine these two and they just call it delta H of hydration. Okay? Enthalpy of hydration is always negative. It's always an exothermic. Okay, so now that we know that, let's look at this here. Silver nitrate has a lattice energy of negative 20 kilojoules per mole, okay, and a heat of solution of 22.6 kilojoules a mole. Calculate the heat of hydration of the silver hydrate, okay. The lattice energy, let me come back, PowerPoint. Lattice energy, that's going to be your solute, okay, because you're trying to put silver nitrate in water. Lattice energy is basically the energy it takes to break that, okay? That's going to be negative 820. So lattice energy is another way of saying delta H is solute. So let's write that on here. We have a lattice energy when that just equals to delta H of the solute. And this equals to negative 820 kilojoules per mole. What else do we have here? A heat of solution is 22.6 kilojoules per mole. Calculate the heat of hydration. Okay, wait, which one do we have? Let me write this down. Heat of solution is 22.6. Okay. delta H solution equals to 22.6 kilojoules per mole, and it wants us to find heat of hydration. So delta H hydration equals, we don't know. Okay, so let's write down the formula. Let me put it in this color now. We have delta H of the solution equals solute plus hydration. So delta H solution equals H delta H hydration plus delta H of solute. Right, I think they do it solute plus hydration, but it means the same thing. Yeah. Okay, so let's put all the numbers we have. We know the solute is negative 820. Negative 820. We're trying to find delta H of hydration, so I'm going to put delta H hydration, since that's what we're trying to find, equals to delta H of solution, which we said is 22.6. Okay, notice they're both in kilojoules per mole, so we don't need to convert anything. Okay, so let's bring this over there to isolate this. So it's at negative here, so we're going to bring it over, it'll be a positive here. So we'll have 22.6 plus 820 equals delta H hydration. Okay, have my calculator out. 22.6 plus 820, 842.6. Oops. Delta H hydration equals to 842.6 kilojoules per mole. Okay? And so it's just a simple adding and subtracting. This is very basic algebra, but it's knowing what goes where. So I think the key is when you see delta H of hydration, it's kind of like this new formula over here, where hydration just means solvent plus the mixture put together. And then if you see a solute, that's another way of saying lattice energy. Anyways, that's a way to basically calculate the energy involved in mixing. How much energy do you need? How much energy are you going to get? Solutions over time will become in equilibrium, and this will become very, very, very important. We have like, I don't know, maybe 3 or 4 chapters just over equilibrium. We have an equilibrium constant called K. Okay, and we'll measure the energy involved in equilibrium. But let's just kind of quickly define it right now. And that's where basically the rate of dissolving equals the rate of deposition. So let's think about what that means. Okay, so first everything's going to dissolve really fast. Okay, you're going to put some salt in water and it's going to dissolve really fast. Over time, the dissolving is going to be very slow, and the salt will begin to redeposit, okay, meaning it's going to start forming a solid at the bottom after a while. Okay, eventually the salt rate of dissolving, so the rate it takes to dissolve it, is going to be the rate it takes to deposit it. So basically they're in equilibrium with each other. So the rate that this is dissolving, so sodium chloride becoming ions, so basically dissolving, at the same time, sodium chlorine ions, because you see that they're positive and negative, they're going to be attracted to each other. They want to also form a solid. So this is, do you see the arrow has it going back and forth? That means equilibrium. So the rate at which these are dissolving, becoming sodium chloride ions, is the exact same rate that these are forming sodium chloride salt. Okay, so basically the rate they're separating is the rate they're coming back. So it looks like nothing's happening because the rates are equal, so we say it's an equilibrium. Okay, and we'll go more into this right now. There's different types of solution. There's a saturated solution. This is whenever you've mixed the exact amount that it could dissolve. Okay, remember at the very beginning we said the solubility of sodium chloride is 36 grams per 100 grams of water. So once you have dissolved 36 grams of that salt in the water, that is saturated, meaning you put the max amount of solute you can possibly put in there. Okay? Unsaturated is when you put less than that. So let's say instead of putting 36, which would be the maximum amount, let's say I only put 30. Okay, well I can still add more, so it's unsaturated, meaning you can add more. Supersaturated is when you add more than the amount. And in the next little vodcast thing, I show a video of the supersaturated, which is pretty neat. This is an unstable solution, and basically how you do this, how do you add more, is you heat it. Heat increases the solubility of a solid. Okay, so you're actually able to add a little bit more, and if you slowly cool it, it will stay in solution. Okay, but it's very unstable, so usually if you just kind of hit it, literally just hit the beaker that it's in, all of that like extra salt that dissolved will all of a sudden just fall out of solution. And what do I mean by fall out of solution? I mean it'll all of a sudden become a solid. It's very neat looking, but that's how it works. And here, this is actually how they make rock candy. It's a way of purifying called recrystallization. What you do is you supersaturate a solid, okay, a solution. So you put a solid in there, you heat it up, so you make it supersaturated, okay? And remember, it's very, very unstable. Okay, so what happens is over time, you let it slowly cool. As it cools, that solution will become saturated again. So it's going to basically kick out that extra salt in there. It doesn't want it in there, so that extra salt will reform these crystals. Now, here's the thing about crystals. When crystals purify, when they reform, they favor purity, I guess you can say. So basically, they're going to kick out the impurity. So let's think about this. Okay, so I have a solid, and let's just say it's a very impure solid, and I want to make it pure. Okay, this is how they, like, a lot of drugs and stuff are purified this way. Okay, I want to make it really pure, and I know that crystals prefer to be very pure. So what do? I dissolve all the crystals, and I supersaturate it. Okay, so when they'll supersaturate, then as I cool it, it'll unsaturate because it doesn't like to be supersaturated, and it'll only say supersaturated basically when it's warm. Okay, and now I'm going to reform the crystals. Now, since the crystals prefer to be very pure, when they reform, they're actually going to become more pure. Okay, they're going to kick out the impurities. Now what you do is you keep doing this over and over again. So you keep reforming the crystals again and again and again. And each time you reform the crystals, they become more and more pure until you have something that's pretty much 100% pure. And that's called recrystallization. Basically, you reform the crystals over and over and over to get them more and more pure. We already went over this, the factors that affect the solubility of gases. So remember, it's the opposite. You know, for a solid, you want to increase temperature. But for a gas, you want to decrease it. Because if we increase a gas, think about this, the temperature of a gas, it's going to become more gas-like. We don't want it to become more gas-like. We want it to become more liquid-like. Okay? So what do? We cool it. And as you cool a gas, it becomes more liquid-like, and so it can actually dissolve more. Okay, you can actually calculate the effect of pressure on gas, okay, using Henry's law. Okay, so we want to see basically how much gas do you need in something. Okay, basically what concentration of gas do you get at that pressure. Okay, so remember, if you increase the pressure, more gas will become soluble. Okay, so we're trying to figure out how much gas will you have at that pressure. Okay, how much gas will be soluble if you want at that pressure. Okay, so here's Henry's law. S of the gas, this is the solubility of the gas. So how much of the gas is now soluble? And that's going to be in molarity, in big M, that's the unit you'll get. KH is Henry's constant, so that's the molarity per atmosphere. So basically this is a constant, it's unique for each gas, and this basically tells you the pressure you need per molarity, okay? And then P, partial pressure of gas. So this is the pressure you need, okay? So what pressure do you need to put the gas at to have a certain solubility? Or you can look at the other way. You need this solubility, so what pressure do you need the gas at? So really, you're going to either be solving for S or P. And here's the formula here. So let's look at a problem. what pressure of carbon dioxide is required to keep the carbon dioxide concentration in a bottle of club soda at 0.12 molar at 25 degrees Celsius. Okay, so we have the concentration. Come back to the formula here. We have S, which is the concentration, or if you want, the solubility of gas. Now we're trying to find the pressure. Okay, and this is a carbon dioxide, so 3.4 10 to the negative 2. Okay, so we have, so let's write down the formula. S of the gas, and this is like the concentration or solubility, okay? KH, this is the constant, multiplied by the pressure of the gas, okay? We know the solubility of the gas that we need is, let me go back here, 0.12 molar, right here, okay? I told you the units there will be molarity, 0.12 molar, okay? And let's look at the K of the gas. We said 3.4 10 to the negative 2 molarity per atmosphere. That's for CO2. 3.4 times 10 to the negative 2. So 3.4 multiplied by 10 to the negative 2 molarity per atmosphere. Okay, now let's think about this. We have a molarity right here and a molarity right there, so those will cancel, okay, and leaving you with what? Atmosphere. Okay, so let's play everything in. We have 0.12 for S. We have K is 3.4 times 10 to the negative 2. And we're trying to solve for what pressure do we need the gas at. Well, this is multiplied here. So when you bring it over, over here, it'll be divided. So if we go 0.12 divided by 3.4 times 10 to the negative 2, we'll get the pressure of the gas. So let me see. We have 0.12 divided by 3.4 times 10 to the negative 2. The pressure we need, pressure of the gas, is 3.5 approximately atmospheres. Okay, so again, that'll tell you kind of what pressure do you need to get that gas that's soluble, or if you know the solubility, what pressure do you need for a gas. Let's look at another example here. Not there. First, let's think about this. Okay, some laboratory procedures involving oxygen-sensitive reactants or products, okay, call for using a pre-boiled water. Why? Okay, so let's think about this. Something is sensitive to oxygen, okay, and a lot of times you can get some oxygen in your water, and we don't want that because it's sensitive. It doesn't want oxygen in there, okay? Oxygen's a gas, right? So why would we boil it? Okay, think about this. When you boil something, what are we doing to the temperature? We're increasing the temperature, right? Now, a gas at higher temperature, is it more or less soluble? Less soluble, right? Okay, so we're trying to increase the temperature so that the gas is less soluble. So if it's less soluble, it's basically dissolving away, it's going away. So when we pre-boil water to get rid of the extra oxygen, what are we getting rid of? Oxygen. And what is our reactant or product sensitive to? Oxygen. So it's sensitive to oxygen. So what do? We get rid of it by boiling it. Anyway, so that's just an application. Let's look here. Use Henry's law to determine the solubility of helium at a pressure at 1 at 25 degrees Celsius. Okay, so we want the solubility, okay, which is S, okay, or sometimes they'll say concentration. We have 1 atmosphere, and let's look at helium is 3.7 times 10 to the negative 4. Okay, what concentration will we have? So we have, down here. Concentration equals K times the pressure. Concentration we're trying to find, we don't know. K, I forgot what I said. For helium, 3.7 times 10 to the negative 4. 3.7 times 10 to the negative 4. That is molarity per atmosphere. and we know the pressure that we're putting it at is 1 atmosphere. So we have atmosphere and atmosphere, so those units are good. We don't have to convert anything. So our final unit will be in molarity. So let's plug this in. Solubility equals to K, which is 3.7 times 10 to the negative 4. Oops, that looked more like a 4. Multiplied by 1, which is our pressure. So that tells us solubility is 3.7 times 10 to the negative 4 molarity. Okay, that's how much we can dissolve. All right, in the next podcast, we're going to go over different ways to quantify a solution, see how concentrated it is. So, we're looking at molarity. We've looked at this before, which is moles per liter. So, this tells us in 1 liter, you can basically dissolve 3.7 times 10 to the negative 4 moles of something, okay? So we're going to look at how to calculate molality. Oh, I have 2 molalities. Molarity. No, I don't. Molarity, molality, mole fraction, mole percent, parts by mass, parts by volume. Okay? So we're going to look at all of those calculations.